The next topic is Fischer-Carbene and carbene complexes, Schrock-Carbene and Schrock-Carbene. We counted these before in the 2000 course. I come back to our table of ligand classification in terms of hapticity. So now we've discussed these two complexes. Next week we're going to discuss those. You're doing a practical on those. Now we're going to discuss these and these. You see, you're not doing too badly. You know, we're sort of starting to cover all these things. Now, this is a revision from the 2000 course, just to remind you. Remember, in the context of hapto-1 coordinated multiple bonding to transition metals, we have two possibilities, carbenes and carbines. Carbene complexes, carbine complexes. These are very important complexes, and they're very important in catalysis, which we're going to see today. I remind you, the classical Fischer-Carbene synthesis we see here, we discussed this last year. We start off with typically a group 6 carbonyl, hexacarbonyl, here shown tungsten, reacted with an alkyl or an aryl lithium reagent. Now you see, you can understand what's happening. Don't learn this. Understand it. What's happening in the first step here? Why does that happen? Can someone explain it to me? Think about nucleophiles and electrophiles. That's all you have to do.
Because the negatively charged nucleophile Me, it wants to bind to tungsten. It does that through
not to tungsten?
COs.
To CO? Why? So what do we have? Think about it.
Because the tungsten is
tungsten pentacarbonyl C triple bond O. This carbon. It's delta plus. Why? Because oxygen is more electronegative. So what happens? The methyl hot nucleophile attacks there.
Yeah.
And when it attacks there, the consequence is that you end up with this intermediate. You end up with this intermediate here. And of course, that's something you could store in a bottle. But what we can now do is we can actually convert that to a classical, this is a methoxycarbene, Fischer-Carbene. So this is revision. We can do this in a number of ways, incidentally. Classically, we employ the so-called Meerwein salts, or the Meerwein salts, which is OB3 plus BF4 minus. That is a methyl transfer reagent, and that would work to install a methyl group on that oxygen group over there. Now, Fischer-Carbenes are great, but I have a statement here that you don't really get real metal-carbon double bonds. Why is that? So let's draw the structure of a classical Fischer-Carbene. M is a group 6 metal. Oh, there it is. My statement is that's not a real metal-carbon double bond, but I've drawn it there as a metal-carbon double bond. Why is that not really a double bond formally? Because of resonance. Because we have two possible resonance structures here. Remember, we've got lone pairs sitting on the oxygen, which can do what? You see, you push the electrons around in organic chemistry, we do the same in organometallic chemistry. Only the systems we study are much more interesting. Plus, minus. You see what's happened there? Boom, boom. These are the two resonance structures of Fischer-Carbenes, assuming that you have a heteroatom here, with ligands capable of sigma donation. In the classic Fischer case, that's always the case, that you have a heteroatom attached to the carbene. Now, we can represent these two resonance forms by the overall resonance hybrid. One can represent it like that. So you see, if you think about it in terms of simple resonance structures, Grenzstrukturen, you will notice that you don't have the bond is not localized between the metal and the carbon. Here we have some density functional theory calculations of Fischer-Carbenes. This is in this case a molybdenum Fischer-Carbene. But you can see here in this back donation that there's a back donation from the molybdenum to the carbon. So this is DFT functional calculations. These are balls or balloons here reflect where the electrons are sitting. And what you see in the LUMO, which is the lowest energy unoccupied molecular orbital is what we have here, right? So that you have this bond delocalization over the molybdenum, or let's say group 6 metal carbon O functional group. In contrast, Schrock carbines tend to have real metal carbon double bonds, right? Because you don't have, in a Schrock carbine, in the classic Schrock case, you don't have this possibility of delocalization that we see here. We did this in the 2000 course, I remind you. The synthesis of a classic Schrock carbine is shown there. We have the reaction of, in fact, tantalum. Basically what you do is you take tantalum pentachloride and you react it with 5 molar equivalents of lithium neopentylamine, we call that. It's an organolithium reagent. This morning we were discussing that. What's going to happen if you do this reaction? Yes. What are we going to end up with? Yes. By metathesis. Shown there, but I'll just draw it again. Now the tantalum doesn't like that. Now, you know, some people have studied this. This is not really how the reaction goes. It's a little bit more complicated, but didactically I think it's fine to do this. This is a tantalum with mega steric crowding around it, right? Because these are very sterically demanding groups, and that makes the situation untenable for the tantalum. And what does it do? It does an alpha H elimination, and you end up with that. So that is a typical Schrock carbine. What we've discussed now are 2 classical cases, Fischer and Schrock. Now the way to think about this is that Fischer and Schrock carbines, now this is an important point, right? We've looked at these 2 classical cases, and this is how far we got in the 2000 course, and I think it was already quite far. But these are just the classical examples. There are a plethora of carbene complexes that exist, thousands of examples. And to classify, not every carbene complex that exists necessarily can be categorized as Fischer type or Schrock type. It's not like we have 2 drawers into which all of the carbene complexes known can be put in. These are just 2 extreme cases. It turns out that most, or not most, but many carbene complexes that have been isolated actually fall somewhere in the middle. They have characteristics of Fischer carbines and characteristics of Schrock carbines, and so they sort of exhibit the reactivity of both, right? Now this table over here, again, describes the characteristics of Fischer and Schrock carbines. I mean, if we assume the classical case, right, like we've looked at, these are classic examples. And we can represent, we tried to do that this morning in a tutorial, using the Dewar-Chat-Duncanson model, DCD model, the difference in terms of the bonding interaction. So you can think of a Fischer carbine essentially as being a neutral donor pushing electron density into a d metal. You have a pi back bond. Whereas with a Schrock carbine fragment, you can think of it as being something like that. So here are some characteristics of Fischer and Schrock carbines and their differences. And typically in a classical Fischer case, we have a heteroatom attached to the carbene-carbon atom. We don't have that in the case of the Schrock case. In the case of a metal carbene complex of the Fischer type, the carbon atom of the carbene tends to be electrophilic. This is an important distinction. And in the Fischer case, tends to be nucleophilic, right? So that's an important distinction, which is not shown in this table. But in the classic cases, a Fischer type carbene complex has an electrophilic carbon atom, and a Schrock type tends to be nucleophilic. Okay, now that's important. That's an important point. Also, something which we looked at in the 2000 course is oxidation states. Generally, a Fischer-type carbene complex has a very low oxidation state, and a Schrock-type carbene tends to like pull all the electrons over. That's what you see here. What it's actually doing is it basically steals all the electrons from the metal, essentially. All right. Now, I want to, I think those are important points. Now, like I just said, don't think, and this is a mistake many students make, even advanced students, that there's just two drawers, Fischer and Schrock, and every carbene complex you make must fit into one of those two drawers. No. Sometimes you have complexes that exhibit, in fact, characteristics of both. Here is a very nice example. This is a rhenium carbene complex. This rhenium carbene complex is CP2, so that's cyclopentadienyl rhenium CHPH. Now, if we look at that, we would be tempted to say, based on this table, that, well, there's no heteroatom sitting on the carbon. Rhenium is obviously at least in an oxidation state of +2 because there's two anionic ligands there. I would say it's Schrock type. Looks like it, right? You see that? If you had to identify it. But another characteristic of a Schrock carbene is that the carbon atom in the carbene carbon atom is nucleophilic. Now it turns out if I take this complex and I react it with trimethylphosphine, the product is this. So tell me what's actually happened there.
Must be electrophilic.
What?
It's actually electrophilic.
Exactly, because Pb3 is a nucleophile, and it's attacking, apparently, a carbon atom that's electrophilic. So that suggests it's in fact Fischer type.
Yeah.
Now check this out. If we react this with HCl, you get this as a product. Yes. No, sorry. It's not the product. No, sorry, that was right. Yeah, that's the product. You get a rhenium, formerly rhenium 4 complex.
Okay.
Well, what's happened here?
Taken out.
Here it's behaving as a nucleophile. Otherwise, if it was behaving electrophilically, it would pick up the chlorine.
Yeah, yeah.
So this reaction tells us that in fact the carbon atom is behaving electrophilically. So you see, the point is, don't lose yourself in the details. I'm just using this to illustrate that some complexes exhibit characteristics of both. I mean, in terms of the substituents on the carbene, as an H and a pH, the rhenium is in an elevated oxidation state. The simplest thing to say is, oh, it's definitely Schrock type. But, I mean, because that doesn't look anything like a Fischer type carbene. In a classic sense, there's no heteroatom. But at least one of the reactivities suggests that the carbon atom is electrophilic, i.e. Fischer type. So the point is, very often you have to look very carefully at the reactivity of a carbene complex and look very carefully at the bonding situation of which you have to study by various methods, for example, density functional theory, to really categorize it. And what you often find is it's neither Fischer or Schrock type, it's somewhere in the middle. All right, so that's a very interesting and important philosophical point. Now, I want to now extend our toolbox using the notes of Fischer. So if you complain, it means that you're complaining about a Nobel Prize winner. Well, these notes have been, of course, adjusted, right? So, yeah, the ultimate start was in Munich. Now, we've looked now at basically two ways of making Fischer and Schrock type carbenes, right? The classical examples. Don't look so sad. You look very sad. Is everything all right?
No, I'm happy.
All right. I want to now extend our toolbox, because remember, today is about building tools to make molecules and understanding them. It's great. It's exciting. All right. I want to now look at some other ways that we can make carbene complexes. I'm going to start off with classical Fischer types. So synthetic groups to Fischer carbene complexes. And I'm going to look at some selected alternatives. We've already looked at the classic case, so this would be a second possibility. This is quite interesting. This is from electron-rich alkenes. Now what we do here, this is a beautiful reaction. Here's an example. We take, for example, molybdenum hexacarbonyl, and we react it with something like this. This is an electron-rich alkene, because it contains these electron-pushing amine groups. So that's an electron-rich alkene. And you know what you get? Believe it or not, you get minus CO, you get CO5 molybdenum C and R. Now, the reason why that reaction goes is because of something called the Van Slyck equilibrium. Van Slyck was incidentally a scientist at the Technische Universität Berlin, where I did my postdoc. And he came up with this equilibrium in the 1960s. Basically, if you have an electron-rich alkene, what that actually does, according to the Van Slyck equilibrium, is it generates free carbene fragments. Now, if you have a carbene fragment, what's going to happen if it sees molybdenum is it's just going to attach itself to the molybdenum. Obviously, it's going to decarbonylate, push off one of the COs, and then you get the. So that's one way of doing it. You can, of course, also use electron-rich alkenes or olefins that have different numbers of. You can also use 6-membered rings. You can play around with the R substituent. This tends to work with group 6 metals very well. Another synthetic methodology is using. This is my personal favorite, photolysis and diazo compounds. We actually saw that in the lecture on a moment ago, the lecture on alkyl compounds. Remember, you can have a carbene insertion into a metal H bond, and that's a way of making alkyls. This is something similar. So this is now a third synthetic tool from diazo compounds. So what happens here is, for example, CP molybdenum tricarbonyl. If we photolyze this in THF, what actually happens is the carbonyl is photolytically extruded, and we get a hot reactive molecule where the THF coordinates to the molybdenum. Oh, sorry, this is manganese, not molybdenum. Coordinates to the manganese center. Now that's a very weak coordination. Let me maybe just draw it for you. So this is CP is cyclopentadienyl. It's a piano stool complex. That's what it looks like. Now if we react that with something like this is the classic example. So this is the diazo compound, right? CPH2, a diazo compound. We lose dinitrogen, that's entropically driven, and what's the product going to be? If I lose dinitrogen, what do I generate? I generate a free carbene fragment, don't I? Looks like that. And what's that free carbene fragment going to do? It's electron deficient. What's it going to do? So where's it going to go?
It's electrophilic, isn't it?
It's highly electron deficient. It's count the electrons. There's only 6 electrons there. So if I strip off the nitrogen, I end up with that. And what's that going to do?
find more electrons.
Find more electrons where? Manganese, yes. So what it does is it basically substitutes. So nucleophilic substitution goes, I mean, it is electron deficient, but nucleophilic. I mean, that sounds a bit strange. But the thing is, this lone pair here can act as a nucleophile, and it attacks the manganese center, although it's electron deficient. I bet you've never heard of something like that. Something that's electron deficient but nucleophilic. That's what a carbene per definition is. It's both. Anyway, it attacks the manganese center, and the product is a carbene. You see, now here's another example of a complex that could potentially be, plus 3THF, potentially be either Fischer or Schrock type. You have to look at the electron structure, and also look at it on the basis of reactivity. It's also possible. This is also quite a cool reaction. To take, so this is from dianions, or let's say from dianionic species. So let's take this complex as an example. So this is a disodium pentachromate. So in fact, this is really essentially a chromium CO5 2-. You get those. So that's an example of a homoleptic chromium carbonyl that's actually got a 2- charge. Now, what's going to happen if I react that with this? What's going to happen? It's a dianion. Chromium pentacarbonyl 2-. What's it going to do? Well, what it's going to do is it's going to eliminate 2 equivalents of sodium chloride, and believe it or not, you get this. Makes sense. Because this is these are chlorides. This is an anion. You can think of it. This is a highly electrophilic sense. It's all about nucleophiles and electrophiles. I get the feeling you guys don't really understand that, right? Nucleophiles and electrophiles. And if you don't understand that very well, you're lost, right? So revise that from organic chemistry. Anyway, it's a metathesis reaction, and you end up with that product. So that's another tool that we have, and there's numerous others as well, which I'm not going to go into. I just wanted to give you and show you the idea that, in fact, there are other synthetic strategies to making Fischer carbene complexes. Now, we also have many other tools, by the way, or many other synthetic strategies to make Schrock carbene complexes. But I'm not going to discuss that right now because we're running out of time. But what I will do is look a little bit at the reactivity of carbenes. Now, I've already said to you that one of the key things is if a complex has a Fischer-type reactivity, a nucleophile is going to attack the carbon atom of the carbene because it's electrophilic if it's Fischer type. And if it's Schrock type, what's going to happen? Exactly.
Yes.
Let's look at some selected examples of highlighting these facts. So, let's start off with the Fischer carbene. So now we're looking at reactivity of carbene complexes. Now, let's start off with the classic Fischer carbene. All right. If I react this with we've already seen this reaction, and it's behaving Fisher type, what's going to happen? Come on, someone, what's going to happen? Right, because in a Fisher carbene, this is an electrophile. This is nucleophilic. In fact, we get exactly that. It's called an illid. And basically, it is a charged species. Sorry, yeah, that's right. So that's an important reaction. And that highlights, again, the fact that it is Fisher's shock type. Now, sorry, it's Fisher type, yeah. It's Fisher type, because it is clearly a Fisher carbene. Now, let's look at some more examples of Fisher carbenes. What do you think would happen if I take this Fisher carbene and I were to react it with lithium pH, for example?
Well, that will make pH nucleophilic.
Yes, the pH minus is a nucleophile. Where is it going to attack? Yes, so what are we going to get as a product? What we're going to get, nucleophilic attack on the carbon, you're going to get something like this. A salt. So you basically get an anionic intermediate, right? You get an anionic intermediate. And what would happen if I were to now react that, for example, with H pluses?
Oh, H plus is an electrophile.
Yes. So where's the only nucleophile there in that whole molecule?
Oxygen.
Yes, yes. And if that oxygen picks up the H, what's going to happen?
It's going to release R dash.
No, it's going to release what?
Alcohol.
Yes, and what are we going to be left with? A new carbene. A new carbene. How cool is that? This is how you can actually basically get rid of this pesky alkoxy group in Fisher carbene chemistry and put on a decent substituent plus HOR prime. What would happen, you see, you can figure this stuff out. You don't have to learn it. You can understand it in terms of nucleophiles and electrophiles, everything. Everything in chemistry. I don't want people whining, saying, oh, we had to learn all these reactions. You don't. You can understand them in terms of simple nucleophiles and every reaction. Let's do another one.
The one above, can that also have hydride addition?
Yes, that's a very interesting question. Yes. In principle, yes. I don't actually know if someone has actually done that reaction.
Or is it because it's anionic in the next one that it can?
Well, basically you'd end up with this, right? I think that would be very, very, well, it would be very reactive, of course, because you've basically, I mean, that would probably be unstable. It's a very good question. Something that one could try, right? That's the beauty of this. You can come up with these ideas and try them and see if it works. Principally, I think it might be possible, but it would be very, very reactive because that's actually, this is a dative bond. This is a weak coordinative bond, right? So that thing would probably fall apart. Now, what would happen, do you think, if I take a Fisher carbene, again, in terms of nucleophiles and electrophiles? I don't want you memorizing reactions. And I react this, for example, with NH R2, an amine, an organic amine. What's going to happen? What is NH2R?
Nucleophile.
Yes, it's a nucleophile. So where is it going to attack? In a Fischer carbene
The
complex.
carbons.
Yes, and what are we going to get?
And
We're going to get something like this.
carbon one.
Oh, yeah, it's R. As an intermediate, isn't it? So it's going to be something similar to what we have up there. And then what's going to happen in the second step?
Elimination of
Hydrogen?
Elimination of?
the hydroxide.
Hydrogen elimination.
Alkyl.
We're going to eliminate HOR and we're going to get an amino Fischer carbene. There we go. You see that? You can predict the reactivity. All right, so that's some selected reactivity, and all of these things can really be rationalized on the basis of nucleophiles and electrophiles. That's all. That's all it is. Now, I want to discuss some very important. We're not going to get time to discuss carbine complexes today. We only have 15 minutes left. I want to discuss something of paramount importance now concerning reactivity. And what I want to discuss is two topics in the last 15 minutes of the lecture. I want to talk about something called the Tebe reagent. Now we're talking a little bit more about Schrock again. We've been talking a lot about Fischer. I want to talk about Schrock. Now, the Tebe reagent is a beautiful reagent that in fact converts. It's a methylene transfer reagent. Now, I don't know if you've done this in organic chemistry, but who's heard of the Wittig reaction? Wittig? Wittig.
Yeah, I think it's like white.
What is the Wittig reaction? The Wittig reaction is where you take something like that and you react it with something like this. That's called a Wittig reagent. Triphenylphosphine CH2. Have you seen this? You should have. And what you get out of this is R CH2H plus PH3P double bond O. It is a very important reaction in organic chemistry where essentially what you're doing is you exchange an aldehyde, for example, with a CH2 group. How does it work? Well, the mechanism is something like this. You have R, and what happens is you have, this is a delta minus, this is a delta plus. The CH2 right, basically comes and sits here, and what you have is something like this. So you get, this is an intermediate, and then it happens again. So these are called 2 plus 2 2 plus 2.
We didn't do this in the course, but I did it in the paper. That's why.
You did it in?
In the paper we had to write, I used this.
Yeah.
But I don't think we did it in the course.
So this is a 2 plus 2 cycloaddition. Yeah, that's why I'm just revising this. Well, you should have done this anyway. So you get that, and then you go, sorry, this is an R, so what's the result of that? These are very important, these cycloaddition reactions. The result is that you end up with this double bond plus what? PH3 double bond O. That's the mechanism. That's how the Wittig reagent works. The Wittig reagent is a methylene, a CH2 transfer reagent. It's a beautiful reagent, classically in organic chemistry, that converts alkenes to, aldehydes to CH2s. This is old-fashioned organic chemistry. Now we have something even better. in inorganic chemistry and in the context of carbenes, and it's called the Tebe reagent. And it's like a Wittig reagent on steroids, meaning the problem with a Wittig reagent is it only works in limited cases. It doesn't always work. For example, if you have acid anhydrides and stuff like that, it won't work. It only works with aldehydes generally or some ketones. The Tebe reagent works with any. If there's a C double bond O, you will get a CH2 group if you use the Tebe reagent. So this is a very important reagent. Tebe, and how do we make it? We make the Tebe reagent in the following way. It's based on titanium. And if I react this with aluminium trimethyl, two equivalents, remember that is a methylene transfer reagent. What you get out of this reaction is a crazy molecule. Don't worry, we'll discuss this in a minute. You get this thing here. Now what basically happened there, you reacted with two equivalents of aluminium trimethyl aluminium. This stuff is really hectic. I mean, this is a very powerful alkylating reagent. And of course, like we saw in lecture 1, it will alkylate. You'll get metathatical exchange and you'll install a methyl group on there. Basically what you form is, the important thing is that you form this thing here. Alright, so what's actually happened here? What's actually happened here is the following. Let's think about this. The aluminium trimethyl is very Lewis acidic, right? Very Lewis acidic. So it pulls off this chlorine and you form aluminium chloride Me3, right? Yes?
Could you say that again, sorry? I didn't catch that.
Aluminium trimethyl is a Lewis acid,
Yeah.
right? I mean, you use it as a catalyst in various organic reactions, right? It's
Yeah.
highly Lewis acidic. So it abstracts the chloride here, so you form, if you will, AlCl Me3 minus. Yeah. And then, of course, the methyl group on the aluminium goes on to the titanium. Right, so that's sort of the first step. Right, that's how we get that byproduct. So that's what we get, all right?
Yeah.
And then what actually happens is we've now generated this thing over here with the first equivalent of the, do you all follow that? It abstracts the chloride and alkylates it. Now this thing is generated. And it's going to react now with another equivalent of trimethyl aluminium. And this was actually quite an interesting reaction. What actually happens here, okay, it's a little bit difficult to visualize, but this is Lewis acidic. This is Lewis acidic again. And what it does is it actually pulls off the hydrogen on this methyl group, pulls it off. Check this out. Pulls it off, making that a CH2, right? Watch this. The H is pulled off, goes to the aluminium, right? You see what's happening here? And we eliminate methane. And what are we left with? We are left with AlCH32, and we form then this bridging complex here. So that's the mechanism of how this thing is formed. That's one of the mechanistic rationales, if you will. Chloride abstraction from the Lewis acid, followed by alkylation, and then in a second step, this in situ formed thing here reacts with another equivalent of AlMe3, CO3 and effectively forms this here. That's
Aluminum chloride bond form?
Oh, the aluminium chloride bond forms because this, if you think about this, what you have here is an electron deficient aluminium with two CH3 groups and a bond to this bridging methylene. We call this a bridging methylene. And that bridging methylene, and so the aluminium is hungry for electrons, right? It's got 2, 4, 6, and it sees this chlorine. It sees this chlorine, which has, of course, lone pairs, and it forms a dative. It grabs it. So this is a dative bonding interaction. But that's the Tebe reagent. Now, that's the Tebe reagent. That's how you generally generate this in situ. Now, what actually happens with this thing, right, and this is quite interesting, is that it is a source. You can think of this, if you will, of being in equilibrium with this thing here. So you can think of the Tebe, so this is the Tebe reagent. You can make it and put it in a bottle. But if you put it in solution, it can principally, you can have cleavage of this titanium chlorine bond, and you basically form a titanium carbene, you see that, and the aluminium dimethyl chloride.
But aluminium is again electron deficient.
Yes, it's electron deficient, but I mean that's not too much of a problem because, well, of course it's not ideal. It's not ideal. In fact, this will probably dimerize or something. Point is that this reaction, the equilibrium will certainly lie way to the left, right? But the point is there is an equilibrium. And this is effectively a source of this. Now this thing here is very reactive. And it is Schrock type. Now if I take the Tebe reagent, and I take this reagent and I throw in acetone, what's going to happen? Think about this, and think about this. If I take that, and I throw in acetone, what are we going to get as a product? Alkene. Yes. Mechanistically, how is that going to work? Mechanistically, it works as follows. Where's the board duster? For God's sake.
Duster.
Mechanistically, like I just said, the Tebe reagent effectively is a masked form of generating this hot methylene transfer reagent. And this thing is now going to see, here's acetone. Now, remember, it's Schrock type. It's Schrock type. So this is going to be nucleophilic. And how is this ketone going to sort of coordinate to the titanium?
CH3, oh, sorry, the C double O, the C from the C double O, that should be fine.
Is that going to coordinate like this or the other way around?
Double bond to the carbonyl carbon.
It's going to coordinate like this. It's going to basically do this. Why? Because this is electrophilic, this is nucleophilic. This, because it's efficient, because it's a Schrock type system, is nucleophilic. So you're not going to have the ketone approaching it this way around, because then it's a nucleophile and a nucleophile, so it goes that way around. You see that? Nucleophiles and electrophiles, all you need to know. And then what happens is we get this 2+2 cycloaddition reaction. And we get CP2 titanium. This is now the whole mechanistic rationale. This is an intermediate. Following the 2+2 cycloaddition, and what happens now? It goes once again, another 2+2 cycloaddition. And what are the products? The products are Cp2 titanium oxide, which exists as a dimer, and what?
The alkyl.
So this is a reagent of enormous value in also synthetic organic chemistry. You see, we organometallic chemists make all the reagents that the organic chemists use. More and more, all these reagents are organometallic reagents. All right, I think we're going to stop at that point. I mean, we're going to continue next week, I think, with the second part of this lecture, which is going to be Schrock type carbynes. And we're going to be we're a little bit behind. That's okay. I think we covered quite a lot today, and I want to discuss next week in detail alkene metathesis reactions, which is another very, very important reaction associated with carbynes. Also, we have a task associated with that. So I think we'll take next week's lecture to finish this up, the first lecture, and the second lecture will be then on. So we move, so the time schedule is shifting a bit, because I think it was a bit overly ambitious to do everything I wanted to do today. So next week, carbynes and more reactivity on alkylidene complexes or carbene complexes, and we will go for, in the second hour, for cyclopentadienyl reactions. And yes, that's all for today. So, auf Wiedersehen und alles Gute.